Hello everyone, welcome to CS with Aris. Before we start talking about machine learning, let me ask you all something. Let's say there is an ML model and we send some numbers as inputs to that model. The numbers are 0, 5, 25, 50 or 50,000, 100,000. So the question is, what do you think? Will that model be able to attach meaning behind these numbers? Like do these numbers represent temperature of a place or age of a person or salary of a person? Well, I believe the answer will be no. And why is that? Because to an ML model, a number is just a number. A model all by itself is completely unable to attach any meaning whatsoever to any number. In today's video, we are going to see how does ML models actually look into numbers. And by the end of this video, you will develop an understanding of how to prepare numbers before we send them as input to our models. First, let's check out the roadmap for this video. This session is basically divided into 9 small ideas. And in each idea, we fix one common misconception that people usually have about numbers in machine learning. Let's start with point number 1. Before we start talking about ML algorithms or loss functions or gradients, there is one common misunderstanding that we need to clarify. When we humans look at numbers, we see values, but that's not the case for a model. For a model, a number is not a value, it's actually a force. And what do you mean by that? Let's check out with an example. Let's say there is a person whose age is 22. So when we say age 22, we understand as humans that it's a young person. The salary of this person is 90,000. So when we say 90,000 salary, it just clicks that it's a decent salary. It's a good salary. But when a model sees 22, a model doesn't know whether it's an age or a young age or an old age. When a model sees 90,000, a model doesn't know that it's a salary, a good salary or a bad salary. A model just sees a number as a number. For a model, a number is a small number or a big number. A model just compares number with one another. And this big number or small number is basically the magnitude of a number for an ML model. Magnitude of a number here means the influence of a number during the predictions made by the model. So bigger the number, the higher influence that number has. Smaller the number, the least influence that number has. Let's take an example. Let's say we have here 0, 10, 20, 30, 40, 50, 60, 70. We have these numbers. Now out of these numbers, 70 will have the highest influence in the predictions made by the model. 10 will have the lowest influence. Okay, and 0 here will have absolutely no influence. And this collection of numbers is basically called the range of numbers. Now we know that a number is bigger or smaller as a result of comparison. But what about comparison of ranges? Let's say there are two ranges but with different magnitude of numbers. For example, we have two features. Feature 1, it's represented from a range of 1 to 100. And then we have feature 2, which is represented from a range of 0 to 1. These are two features. Now let's say we are calculating 10% of value of both the features. So this first feature will give a value of 10, whereas the second feature will give a value of 0.1. So what do you think? What will be the impact of this 10% value of both the features on the model? Will it be same or different? Well, as we just learned, a model looks into the magnitude of a number, not a meaning of a number. So for a model between 10 and 0.1, 10 will have a greater influence on the prediction. 10 will dominate. It does not mean that feature 1 has more influence or more importance than feature 2. It's just that model listens more to loud numbers, not meaningful ones. Numbers in a model basically behave as forces that push predictions either in upward direction or in downward direction. Bigger the number, upward push; smaller the number, downward push. So ML models don't understand what a number means. It only understands how strong the number is. Let's now talk about 0. In normal mathematics, 0 is just another number. But in machine learning, 0 is a very loud signal. Most of the time in data, 0 does not mean small. It means that no value exists. No orders, no purchase, no clicks, just nothing. For a model, absence means information. So what kind of information? 0 signifies the empty influence of a feature in ML model. When a feature's value is 0, during the prediction in the model, that feature is basically switched off. That feature basically has absolutely no impact in the prediction made by the model, all because its value is 0. The model behaves as if the feature does not exist at that data point. Let us better understand this by taking an example. Let's say we have assigned some weights W1, W2, W3 and W4 to a feature. But if the value for that feature is 0, so the final outcome when we multiply this weight by 0 will be 0, whether we multiply W1 or we multiply W2. Similarly for W3 and W4, when we multiply by 0, the outcome will be 0. 0 basically silences even the loudest of the feature. The way a model learns is by feeding data into that model, and 0 basically signifies no signal most of the time. So if the data that we are feeding into the model has so many zeros, then the model will find it very difficult to make sense of the patterns. Pattern here basically is the data. So we can say that 0 is not neutral. In fact, 0 is very decisive, as 0 means absence of information. So the model completely ignores that feature whose value is 0. And let's take an example to quickly understand how does 0 actually impact the prediction of a model. Let's say we have an ML model that predicts the housing prices. And we all know for a house which has a parking, the price is higher as compared to a house which is without any parking. So let's say we have here house 1, house 2, house 3, house 4 and house 5. We have 5 houses, and out of these 5 houses, let's say H1 is having a parking, H2 is having a parking. For H3 we are not sure whether it has any parking or not. H4 does not have any parking, so we can say no parking. We know that we don't have any parking for H4. Similarly for H5 we are not sure about the parking. Okay, the data that we are feeding into our model is unsure. Now let's say as developers we make this rookie mistake. H3 and H5 are not having data for parking, so we say, let's say it has 0 parking. It has 0 parking. and let's say h1 had 1 parking, h2 had 2 parking. Okay, and this is no parking, so it's obviously is 0. So what will happen at the time of prediction? So as we know, just discussed, parking influences the price of house. So since h1 is having 1 parking, so let's say its price is, for example, 100. Since h2 is having 2 parking, let's say its price is 125. This is just for example. H4 has no parking, so we can say its price is 80. Okay, now for h3 and h5, since we did not have any information regarding parking and we marked it as 0 parking, even its house price will be predicted as 80, which is completely incorrect. For example, let's say h3 had 3 parking in reality and h5 also had 3 parkings. So ideally the price of both of these houses should have been 150, suppose, but the model predicted as 80, nearly half of what it should have been. So this is the negative impact of assuming 0 for a data value which we had no idea about. Now let's talk about direction of a number. So far we have discussed about how strong a number is, that is magnitude. But what about direction? Like, two common signs associated with a number are positive and negative. Positive number basically pushes the prediction upward. Okay, let's for example we say we have multiple orders, let's say 100 orders, 200 orders, 300 orders. So it basically pushes the prediction upwards that okay, this particular product is higher in demand. Okay, the demand of this product is increasing with time. Okay, now let's talk about negative number. If the number is negative, then it will pull the prediction downwards. It will have a pull effect. The positive number had a push effect, okay, whereas the negative number is having a pull effect. Let's take an example. Let's say we have a product, okay, and we have added some discount to it, let's say 25% discount. This 25% discount is basically pulling the price downwards. The price is reducing for a product. So when we will calculate the total sale of that product, the price, the total amount will be lesser as compared to the case when the product was selling without any discount. We know that a model basically compare two numbers. It does not understand the meaning behind those numbers. So while we were discussing our point one, you remember we had two features. One had a range of 1 to 100, another one had a range of 1 to 100,000. So if for a 10% change, the feature 1 will give a value of 10, whereas 100,000 will give a value of 10,000. And for a model, 10,000 is always greater than 10. So we need to be very careful when we are selecting ranges. These two ranges are very different for a model. Why? Because a model does not understand units. When a model compares two numbers, it basically assumes that both of these numbers are comparable. Because model has by itself implicitly no idea regarding units of those numbers. Let's take an example. 1 year of salary, 1 click, 1 mark, 1 degree temperature, they all mean same thing to a model. One, a model does not understand mark, a model does not understand order, it does not understand degree or temperature. It just assumes they are one. They are on same scale of comparison. So the question here is, how do we solve this issue? Like, for us it's very different, and this is because we as humans, we can identify unit. Okay, when we see a report card, we can say that this one is about marks. Okay, when we see any weather forecast, for example, when we see one, we know that this one is related to temperature, so its unit is degree. When we are checking data of any e-commerce site, Okay, let's say we have placed a product on a marketplace, and when we see one, so we know that this is some about related to the orders that our product has received in the day. But a model doesn't understand units. When we try to create a range, a scale, and we want to represent each and every number on this common scale, we need to first process this data in a common numerical language. Okay, so that post processing, when we will place this data, or we can place this data on one common range. So at that point of time, the two numbers that a model will compare will actually make a sense. Let's see it with an example. Let's say we had 1 year of experience. We have 1 degree Celsius as temperature. We have one order on a marketplace. Let's say we use some what we can say, sort of a formula, custom formula, by applying weightage. That's we can assume. And let's say that assumption, using that assumption of that formula, this comes as 0.02, this comes at 0.001, one order comes as 0.1. Now we can place this on a scale of 1 to 10. Okay, now when we compare 0.02 to 0.001 and 0.1, they will make sense. We can say that one order, its value is greater than 1 year of experience, and whose value is greater than 1 degree Celsius of temperature. This is just an example. Okay, so the point here is we need to bring our numbers on a common range, on a common platform, for us to, for a model to correctly compare them. This will result in all the different units disappearing, but the relative impact of all these numbers will remain intact. Now let's discuss a case of a very special number, which is part of the data being fed into our model. Now the unique thing about this special data is it is way beyond the expected range of the number which ideally it should have been. Let's understand this with an example. Let's say we are calculating the average score of students in a class, and the number range is between 1 to 100. Let's say we have 5 students for simplicity. We have S1, we have S2, S3, S4 and S5. Now S1 scored 90 marks, S2 scored 80 marks, S3 has scored 85 marks, and S4 has scored 95 marks. Now if we add all these numbers, it's 90, 180 and 160, 240, 340. It's somewhere around 350. And once we divide it by 4, it should be somewhere around approximately 88. This is approx, okay, which is correct. If we are taking an average, 88 around is correct looking into the numbers. Now let's say this S5, accidentally this score is, let's say, minus 100. Minus 100 is beyond our range. We did not expect it. So what will happen? The total now will drop to 250. And once we take an average will be 50. So as you can see, first one is 88. The average basically dropped to 50 from 88. So it's nearly, we can say, 40 to 50% of reduction in the prediction. The prediction has dropped drastically because of this outlier. Which is outlier here? This minus 100 is basically outlier number. So this one extreme score basically results in a huge error in our system as compared to other numbers. This is the negative impact of such outliers. Numbers don't need to be just integers in our data. They could be real numbers, numbers with decimals. Now, it might look as a smarter move to have as many decimal numbers after the point as possible. Of course, like more decimal numbers mean more precision. But in reality, more precision is just a noise. It does not give accuracy. Let's better understand with an example from our history. Gulf War 1991. you know let's first understand in a very simple manner how does a missile interceptor system works. So American Army had their own missile interceptor system, and that system basically runs round the clock, and it tracks all the incoming targets, okay, incoming missiles. So it predicts the path. Let's say for example, at this point the projectile is here at this place. Now, after t plus n seconds, it predicts that the projectile will be here. And on the basis of this calculation, it also predicts the intercept path. That okay, the intercept missile needs to be shot here following this path to neutralize this upcoming target. Now, what happened back in 1991? These numbers, these data numbers were basically stored as 24-bit fixed point register to store these decimals. So what happened? 0.1 was stored as 0.100001 approximately. Similarly, 0.2 was stored as 0.20000002. Similarly, 0.3. Now what happened after 1 second? Okay, and this calculation was being happening at every 0.1 second, 10th part of a second. So after one actual second, this stored sum ideal it became 1.000015 second. Now that's a tiny difference. Of course, it's 0.000015, so it won't matter a lot. But remember, this is for 1 second, and in 1 hour we have 86,400 seconds. Now let's say, for example, here after 100 minutes, which is 600,000 intervals, if you multiply this 0.000015 by 600,000, it becomes 9 seconds. So this 9-second error is literally a huge error. Okay, let's say ideally the prediction should have predicted that after t plus n seconds the targeting missile should have been here, but the system miscalculated and predicted that the missile instead of here was actually here. So the intercept missile came here rather than here, and this target projectile actually entered the army place and it resulted in casualties. So a good ML engineering practice requires us to have an accurate precision, okay, to use only required number of decimal numbers rather than having n number of decimal numbers. This actually reduces noise and increases the accuracy of our data. Moving on to the next point, each number that we feed into our system must have a specific predefined range. What do I mean by that? Numbers are not magic. Okay, we humans, when we see a number, we can automatically say that this is a valid number and this is an invalid number for this specific feature. We know that, for example, probability can be between 0 to 1. So if we are having data which says that a probability feature could be 1.5 or 2.7 or maybe minus 1.3, we can automatically say that this is an inaccurate data. Similarly, an age of a person will always be greater than 0. We can never have an age of -5 or -10. So if we do not define a specific range, a valid range for each of our feature, then the model, because a model does not understand all by itself that this is a valid number for this feature or this is an invalid number for this feature, a model will consider all the numbers as valid and it will take into its account for processing. Let's take an example of a recommendation system. Okay, for example, let's say you have created a model for Netflix, for example, Netflix or Prime Video or Disney Hotstar, any video streaming service. The point here is this. And let's say you are a user and you absolutely loved Friends. Okay, you are into sitcoms, but accidentally the prediction system calculated your viewing hours as -500. So it predicted that you as a user completely dislike Friends, but in reality you absolutely love sitcoms. So the recommendation system is not going to recommend you other sitcoms like How I Met Your Mother. It is not going to do that. Why? Because of that -500 viewing time of your watching, which was incorrect. Okay, let's say you watched it for 500 minutes. So you ideally should be recommended more sitcoms, but the vice versa happened. So it becomes the responsibility of us engineers to validate the data before it is being sent to the model. If we find any data to be out of range, we must perform numeric calculation to correct it and then only feed that data into our model. So we have reached to the ninth and the final point of this session, GIGO, garbage in, garbage out. So the principle of GIGO states that if we feed garbage into our ML model, what is garbage? Invalid data, incorrect data. So the output that will be generated by our model is also going to be garbage. We have discussed multiple cases of invalid data, like having a negative sign attached to a number when ideally it should have been positive, having zero, having numbers in our data which are totally outliers, way beyond the acceptable range. So data like these become invalid data, and actually the machine learning work starts way before the ML algorithms, at a time when we are supposed to prepare the data to be fed into our machine learning algorithms. The ML model blindly trusts all the numbers, all the data which is fed into it. And it is said that ML model does not fail silently, it fails politely. So in today's video, we did not learn anything about machine learning algorithms. What we actually learned about is how an ML model looks at numbers. A model is unable to identify any meaning behind a number, any unit attached to a number. It only and only looks at a number and it compares only the magnitude of a number. So as ML engineers, before we teach machines to learn, it becomes our responsibility to teach numbers how to behave in the expected and correct manner. As engineers, we must always remember that in machine learning, data is not just an input, rather, it's actually an instruction for the machine. So, this brings us to the end of this video. I hope you guys have learned something out of it. If you like this video, please press the like button and subscribe to the channel for future videos. So, guys, bye bye, tata, see you in the next video.